Hi everyone, my name is Leon Starr, and I am the technical lead of the Toyota Research Institute's Model-Based Systems Engineering team. I'm going to start off by describing our approach to building reference models of the driving environment for autonomous and semi-autonomous safety validation. Based on last year's OSS 5 presentation, we've received a lot of interest in these models as well as our methodology. So I'm especially excited to finally announce that all of our models will be available under the MIT open source license, and that we are actively seeking points of collaboration in the autonomous driving and functional safety community. I will present these details at the end of the presentation. To give you a sense of what our project is all about, I want you to think about how you perform a particular driving maneuver. It doesn't really matter which one, but I've chosen an unprotected left turn in a four-way signalized intersection in the United States. So that's a left turn requiring a yield to oncoming traffic. Now imagine that you would like to explain this maneuver, along with all the things that could go wrong, to a student driver. How would you do it? Well, you could just try explaining it, but I think we all know that a natural language like English is going to fail us in the end. It's just not possible to be precise and unambiguous in characterizing all the possible scenarios you might encounter and how they might interact. But it would certainly be nice if we could build a model of both the intersection or any driving environment and maneuvers within it that could stand as a reference model that we could all agree on. Such a model should not make any assumptions about the design of any particular driving platform. If our models incorporate enough detail to be executable, we might then generate code from this model, and then use that code to monitor real-time or logged driving data and validate maneuvers appropriate to the environment. It is critical that such a model not make any assumptions about anyone's autonomous driving stack or vehicle platform. And it is also critical that we end up with a model that works for all intersections, not just some subset we found in our backyard. As you may have guessed, this is what our project is all about. Before moving on to a more complex intersection driving environment, we'll start with a fairly simple environment and see how we model it. We always take the perspective of our ego vehicle, and here we focus on the lane structure directly in front of it. When we analyze the environment, we label all things of interest, and in this case, we start with RS1 to represent our road segment, our road segment 1. We consider a road segment to be the stretch of roadway between intersections. Next, we label a set of parallel lane divisions. We think in terms of sets, and so there's no implied ordering in the names. We just slap an arbitrary ID on each lane division we discover. To the upper right, we abstract a set definition and name it lane division. It establishes a set which, in our example, consists of 7 elements. We show this particular population with a simple table. Each row represents an instance of lane division. Note that we include the road segment ID since, in a more expanded scenario, we could be looking at more than one road segment. We define a lane as the space between two adjacent lane divisions. From a set perspective, we have a one-to-one mapping among these instances to yield a new set definition called lane. We populate our lane table with these pairs, each of which is an instance of lane. In this manner, we have constructed an abstract model based on sets and mappings and then populated it with perceived elements from a real environment. We typically use the term class, by the way, instead of set definition, but to us it means the same thing. These are not to be confused with a programming class like you might see in a C++ program. So we have the lane division and lane classes modeled so far. It is important not to confuse a lane division with a painted line. They are not the same thing. A painted line is a signaling mechanism for indicating the location and driving policies associated with the lane division. This distinction might not seem important on a sunny day in your particular neighborhood. But what if you are in another neighborhood where lines are painted differently? In the USA, a double yellow line indicates the division between opposing flows of traffic. This convention is not used in many other countries. But the concept of a line marking the boundary of all traffic flowing in the same direction is fairly universal. And if there is ice and snow on the road, the lane divisions don't necessarily line up with the paint anyway. During construction and other activities, there are a number of ways to indicate alternate or temporary overriding lane divisions. Traffic lights and signs are also a signaling mechanism, and we don't model those either. But we do model the information that is being signaled, such as a stop, or caution go, or caution stop, at the appropriate locations in our environment. I cannot stress enough how this filtering on our abstraction ensures that the models can work in any weather and in any region of the world without adjustment. It also ensures that our modeling goals are finite. We can actually get our reference models completed. Phase 2 of our approach is to introduce the ego vehicle into the modeled environment and model a specific maneuver such as a simple lane change. To do this, we identify and model relationships between the ego vehicle and any relevant elements in our environment model. Then we formalize the behavior of any dynamic relationships with one or more state models. Let's take the lane class from our environment. In fact, behind the scenes, we've modeled a more specific version called a driving lane. This is any lane that an ego vehicle flows in, as opposed to an exclusion lane, a parking lane, a shoulder, and so forth. Now we bring in the ego vehicle class. Our ego vehicle isn't always in a position to change lanes. If our ego vehicle is in a parking garage or a driveway, the environment doesn't provide that option. So we narrow that definition down by referring only to an ego vehicle driving on a road. This gives us an on-road ego vehicle, which we can further refine by associating with the driving lane to obtain a traveling ego vehicle. It is always traveling in some driving lane by definition. When this ego vehicle wants to change lanes, it must target an adjacent driving lane in the same direction of traffic. Our relationship to that target lane yields our driving lane change maneuver. The next goal will be to use a state model to formalize the life cycle of that instance, which will define the correct as well as many incorrect lane change behaviors. Before moving on, we need a place to keep parameters that influence the lane change. So we define a driving profile to establish a personality for our vehicle. Part of that profile is our lane change personality, where we can set values for how long we leave the turn signals on before beginning our maneuver, or how long we wait after completing a lane change before initiating another one. In fact, we can instantiate many personalities for our vehicle: suburban, urban aggressive, Swedish, and so forth. Okay, let's define a pattern of behavior for that lane change class. When all things go well, our maneuver exhibits a fairly linear life cycle. We begin the lane change, wait for some period of time for an entry space to open in the target lane, signal our intent for some duration, cross into the target lane, finish indicating, and so forth. The transition from one state to the next is driven by real-world events or expired time intervals. The parameters we saw in the class model establish limits on these time intervals. Of course, things don't always go well. An opening in the target lane may not become available in time, or someone intrudes into our target lane in the middle of the maneuver. Perhaps we cross over the lane division before signaling adequately. We could sit around guessing what could happen all day, but we take a more systematic approach. We build a state table where we consider a response to each event, no matter how unlikely, in each state we've modeled. This process generates a multitude of edge cases, which leads us to a more comprehensive set of failure and recovery scenarios that we can then fold back into the diagram. In fact, we generate our evaluation code from this table, which puts us in an excellent position to report on the coverage of our test cases. We'll talk more about the code generation process a little later. As promised, we're going to move on to the more complicated environment of angular, that is non-circular, signalized intersections. Unlike our Hello World lane example, this is not easy work. Let's take a look at what's involved. In general, we cycle through 3 key steps. First, we do research. We study a variety of example intersections with interesting variations. Since starting at TRI, I've logged a ton of hours scouring through dash cams and Google Street Views, studying interesting road structures from all over the world. But you can only get so far studying. Our approach of labeling elements, abstracting set definitions, and then validating them by filling in interrelated tables is essential to reaching key insights. Now, we're not directly trying to build a case-by-case set of intersection types, and we don't need to look at every single one. Instead, we seek out the smallest possible set of semantic Legos that can be assembled to define any intersection, no matter how complex. This goes for any other aspect of the driving environment. This set of building blocks, along with the rules for snapping them together, is represented by a class model. We then verify that the model we have constructed works not only for the cases we studied, but for more complex cases until we break it. And the cycle continues until we converge on the simplest model that accounts for all our observations. As we firm up our model, we document it extensively so that the assumptions upon which it is founded can be readily questioned. A key aspect of our modeling language is that it exposes our decisions. Unlike a programming language, like say C++, you don't need much expertise in the modeling language to be in a position to find flaws in our logic. Let's take a look at a selected four-way signalized intersection and identify its fundamental components. We start by labeling the intersection itself and then the surrounding road segments. The point at which a road segment meets the intersection gives us an intersection interface. The boundary coincides with the point where a vehicle stops prior to entering, and we have one for each road segment. Each of these instances is labeled as an ordered pair: RS1, road segment 1, RS1-I1, RS2-I1, and so forth. We abstract this concept in our model as a relationship between road segment and intersection. Our model says that any given instance of road segment meets 0, 1, or many intersections. Hollow arrows, by the way, indicate that 0 is a possibility, and the double arrow indicates that more than one instance may be related. 0 is possible since a road segment could originate and end in a dead end or merge onto a freeway or somewhere else. And if a road segment extends from one intersection to another intersection, it certainly meets more than one. We always consider both ends of a relationship, so an intersection must, by definition, be met by at least one road segment, and typically many. Carefully naming and thinking through the multiplicity and conditionality on each side of every relationship has proven to be an extremely productive way to discover edge cases. The pairing up of road segment and intersection instances populates a table abstracted by our intersection interface class. As you'll see, we make extensive use of this powerful modeling technique. Moving on, we'll use the term conduit to refer to a set of adjacent lanes flowing traffic in the same direction. Here we see that there are 4 conduits, each flowing traffic in the forward direction from our ego vehicle's perspective. The other 4 flow traffic in the reverse direction. Now, a conduit flows traffic across 0, 1, or many intersection interfaces, and any given intersection interface is crossed by traffic flowing through at least one conduit, which yields a conduit interface. Note that 4 of our conduit interfaces lead traffic into the intersection. The large branching arrow on the right tells us that we are partitioning the conduit interface set into multiple subsets, 2 in this case. Basically, it says that any conduit interface is either an entrance to or an exit from an intersection. The entrance conduit interfaces are kind of special since they are the only ones associated with traffic signals and those little white movement arrows you see on the pavement. Now, a driving lane, remember driving lane, a driving lane that flows through an entrance conduit interface is what we call an entrance lane, and each entrance lane has one or more legal movements associated with it. We observe that a movement is just well, first of all, a movement's not paint, remember, okay? So it's not the painted arrow. We observe that a movement is just a path from an entrance lane to an exit conduit. To formalize that concept, we just model the many-to-many relationship between those two classes, and voila, we have a table for all our movement instances. This verification part is important. Whenever we discover a road structure that somehow won't populate into the tables, we need to reassess our model. Once again, we identify dynamic relationships between our traveling ego vehicle and its environment, in this case the intersection. To perform an unprotected left, we relate the ego vehicle's current, or active driving lane, to the desired signalized entrance lane, which yields an entrance lane approach. The life cycle of this relationship guides our vehicle to the correct lane and ensures that it waits or proceeds into the intersection based on the proper conditions. It also initializes a relationship to the desired movement. You can see the key elements of this activity illustrated down on the left. Now the planned movement life cycle fires up. Since it represents the overall path through the intersection, it makes sense that it would establish the entrance and exit crosswalks, release the safety gate into the intersection, initiate monitor of priority oncoming traffic, and select the connector which we model as the pairing of our entrance lane to a specific exit lane choice. That's the curved purple line you see in the diagram. The connector traversal lifecycle is always one of 3 types. In our case, we need the yielding connector traversal, since this is an unprotected turn. The yielding connector traversal lifecycle ensures that the ego vehicle yields correctly to oncoming and exit crosswalk pedestrian traffic. Drivers in the USA are familiar with the delicate ballet that happens when there is a combination of oncoming traffic and sudden pedestrians in the exit crosswalk while turning left. This is all part of this connector traversal lifecycle. All 3 of these life cycles run concurrently and are synchronized to monitor and ensure safe intersection transit. And just like the driving environment models, behavior is entirely platform independent. This makes sense because the manner in which we safely traverse an intersection has nothing to do with any particular vehicle or sensing technology or any particular algorithm or machine learning model for controlling steering or determining when and where elements in the environment exist. In short, we believe that formal reference models of safe intersection and traversal of other driving environments is essential for cross-platform validation. I'm going to spend a couple of minutes giving you an overview of how we create code from our models. But I want to emphasize that we get a lot of value from our models without generating a single line of code. Hopefully you can appreciate how a precise and consistent vocabulary that defines the driving environment would be of value for solving problems and defining requirements, as well as anticipating edge cases. You don't need to generate any code to achieve that. The models we build have enough detail in them to be executable. This means that without generating any code at all, you can test the models by hand, kind of like playing a board game, if you just know a few simple rules. In fact, we do that manual execution during early development, but this also means that it is possible to generate code from the models. There are a number of fully open source toolchains that will give you just that, in addition to yielding a variety of helpful testing and validation artifacts. Here's how our process in the MBSE team at TRI works. We express our models using nothing more than a simple text editor. I'm old, so I use VI for everything. The text file has only the model semantics and does not contain any graphical layout information. Also, in text files, we create layout style sheets that establish the placement of all model elements on a diagram in some output format. This system allows us to create and edit complex models quickly and keep them under configuration management. With the models fully specified, we then use a model-to-code translation language called MICA to convert everything into efficient C code. If you're interested in getting a nice overview of our modeling language and understanding how we can translate the models, I highly recommend a book that I wrote in 2017 with a couple of colleagues for A-Press called Models to Code. It's based on a predecessor to MICA called PICA. Hey, I'm not responsible for these names, but the concepts are close enough. MICA is open source, and we'll show you how to find all our goodies on the next slide. Anyway, MICA comes with lots of nice facilities for expressing model-level tests, so you can inject events and process responses to your heart's delight. It also outputs a beautiful PDF that organizes all of your model diagrams, documentation, and the surrounding MICA code, so that you can always have both the models and the code design in one place. We drive these test cases using simulated or actual driving data from our logs. If you want to drive the models from your own logs, you will need to write some code to extract the model-level data, such as events and properties. The test automatically outputs sequence diagrams and some really cool test coverage reports. These reports are really good at showing the percentage of the model exercised during any given test, so that you can quickly see how much behavior has not been exercised. In case you missed this bit from last year's presentation, it's a good demonstration of one way model-generated code can be used for validation. On the right, you see an excerpt from an actual driving log. I'll play that in just a moment. On the left, we have a sequence diagram that was generated by MICA for one of our early lane change models. Remember that the lane change lifecycle has a sequence of ideal states surrounded by lots of failure and recovery states. One of those states is called flag unsafe lane change, and it is entered when we detect a lane division crossing event before we have finished signaling our intention. Now, the sequence diagram tells us the sequence of states actually entered for a given scenario. If any of those states encountered is one of our non-ideal states, we can record that deviation. Okay, let's run it. Here we see that the lane crossed event does in fact occur while we are in the intent indication state. In other words, the vehicle crossed into the target lane before signaling adequately, and we caught it. Imagine the fun we will have with intersection traversals. But we'll have to leave that for a future presentation. We can use reference models of the driving environment to validate and improve the safety of Toyota's autonomous and semi-autonomous vehicles. But since our models are platform independent, we are in a position to make them freely available to the wider AV community. And that is something the Toyota Research Institute wants to do because robust safety validation is critical to the success of our industry. So all of the models are being developed under the MIT open source license and will be opening up our public GitHub site by the end of this month. We'll be posting an article on our Medium blogging site announcing all this in January, so feel free to follow us there. Explanatory videos of our models and our process will appear on the TRI YouTube channel, and we'll post links to them from our wiki. And if you or your organization is interested in collaborating, or you just want to keep in touch, feel free to contact me via email. We have a bit of extra time, so before we go, I thought I would show you a dashcam animation based on our intersection reference models. I threw this together one day so that I could illustrate how you could run the models on live rather than log data in a supervisory validation mode. So I took a dashcam video from Mr. T, that's what I call my Toyota Camry, and then overlaid some animation. All of the animated elements represent instances that would be running in our models if they were in fact live. You will see instance data from the class models and states from the state models changing as we make an unprotected left turn. I want to make it very clear that this is just an animation, and a poorly drawn one at that. This video does not represent any actual software or any kind of HMI. This is simply a dynamic sketch for study purposes that has nothing to do with any real or planned software in any of Toyota's or TRI's vehicle platforms. Oh, and also no animals were harmed. Here we go. Take a look at our dashboard and you can see the designated entry crosswalk there in the middle with some other fields yet to be filled. You can also see a poorly drawn fake paint arrow in the middle of our lane indicating that there are two legal movements from this lane, an inside turn and a through movement. In the upper left of our dashboard, there has been a change of state in our entrance lane approach. The assume stop state has transitioned to a commit stop. This means that our stop-go algorithm has decided that we are absolutely definitely going to stop at this intersection. There's no turning back. We are committed to the stop. To the lower right of the dashboard, we see that the planned movement has been selected as an inside protected turn. You can also see that our exit lane in RS4, road segment 4, will be the one with inside lane division 8, which will be on our left since we are in the USA. In the bottom center of our panel, crosswalk X5 has been identified as our exit crosswalk in our planned movement. By the way, that purplish rectangle up ahead is a virtual barrier imposed by our models called a hold. It emphasizes that our vehicle is not permitted to proceed beyond that point until the barrier is released. There are a variety of such holds that can be imposed, with this particular one being an intersection interface hold. We may not proceed into the intersection until this hold is released. Until the signal changes, we hold at the intersection interface. To the left, we see that all of the lanes in road segment 4 are identified along with crosswalks X6 and X5. In RS4, X6 and X5 are part of the same walk signal span. Neither is occupied, so no crosswalk holds have been placed. The same is true of our entry crosswalk. We do see two holds in front of us, though. In addition to our interface hold, there is an encroach hold. The encroach hold is a precaution to keep us from wandering into higher priority traffic, as this is an unprotected turn. We can see the priority traffic lane from road segment 3 highlighted at the top of our dashboard. It is green since no incoming traffic has been detected. We detect a go signal and a vehicle still clearing the intersection. Note the small delay in the dashboard between the go detection and the change in entrance lane approach state to commit go. Both the interface and encroach holds are released since there is no oncoming traffic. Neither the entry or exit crosswalks have asserted holds either, so we are free to traverse the intersection. The dark purple connector leads us from our entrance lane to the exit lane indicated in the lower right of our dashboard. Great, we've cleared the intersection without hitting anything or anyone, and as we come around, we initiate a new entrance lane approach. This time we are in lane 8 of road segment 4. Note how lane division 8 resolves to the line of cones on our left rather than the cement median edge. Our new entrance lane will be 8, and we'll select the through movement going forward into the next intersection. Now let's do this whole thing again without any annoying pauses.